and Copenhagen, who's going to be telling us about Hochschild homology and the derived Rham complex revisited.
Yep. Thanks, Ben.
Sorry, is it okay to record your talk?
Oh, yeah, definitely.
Great, sorry.
No worries. Yeah, thanks very much to all the organizers for the opportunity. I'm very grateful for it. Yeah, okay, so that's what I'm going to talk about. I have to maybe start on the wrong foot with an apology that I'm not going to talk about K-theory at all in the electronic algebraic K-theory seminar, but I can promise a lot of algebraic theory, so maybe it'll be okay. All right. Let me start by introducing these two families of invariants, which are related to K-theory after all. I'll start with the derived Rham cohomology. And I'll fix a base ring R throughout this talk. Commutative ring. So I'm not going to write the word commutative ever, but everything will be commutative to some extent. Okay. So the first construction is that of the de Rham complex. So if we have an R algebra A, then we can extract this algebraic de Rham complex. Omega bullet. So it's a cochain complex that has some terms. Omega 1 is the Kähler differentials, and the other terms are the exterior powers of it. So that's some explicit cochain complex, and then we can extract its cohomology. That's the de Rham cohomology. And I'm going to use the word cohomology in a slightly non-standard way, I guess. So I want to refer to by de Rham cohomology, I just want to mean the underlying object in the derived category of this complex. So sort of the total cohomology object, rather than in the individual groups. And I'm going to label that without the bullet. And so one thing having an actual complex buys you is a filtration on this object in the derived category. So in this case, it's called the Hodge filtration. It's denoted omega greater than or equal to star, because how do you get these up? So these are also objects in the derived category. How do you get them? You just you just kill some number of the some number of the groups in the beginning of the complex. So you truncate in the brutal way. Okay, so that's ordinary algebraic de Rham cohomology. And then there's a derived version of this construction, which is what I really want to talk about today. So what you can do is you can take non-abelian derived functors and that gets you some new invariant. Now maybe properly it takes in a simplicial commutative R algebra. But you can imagine it's just a normal R algebra if you want. Okay, and what can we derive? So I guess at this point, it's not clear what I would mean to derive the actual complex. Although I'll offer, well, we'll sort of see how to do that later. But at least we can derive the individual terms of the complex. So we can get derived differential forms. I'm going to denote that L omega I over R. So that's what I get by deriving these omega I terms. And the most common or the most important example is L omega 1, which is usually just denoted L. So this is the cotangent complex. And the other ones are derived exterior powers of this one. I can do that, and I can also derive the cohomology object. That's something in the derived category. I can take derived functors of that, and I'll denote that today by L omega A over R, still an object in the derived category. This is derived Rham cohomology. And the Hodge filtration derives as well. Still the Hodge filtration. Okay, so just in case anybody doesn't know what I'm talking about, so this non-abelian derived functors thing, you take a simplicial resolution or of a simplicial R algebra by polynomial algebras, and then you apply the old functor to the simplicial resolution. Okay, so that's derived Rham cohomology, and then the thing that's really going to show up today, the thing that's related to Hochschild homology, is a slight modification of this. So the issue is that this filtration might not be complete. So there's a completion of it. So the Hodge completion. L omega hat. Maybe not. Instead of saying that, let me say what it is. It's you complete for the filtration. So you take the limit of L omega mod the steps in the filtration. Okay, and by mod, I mean you're taking a cofiber or a cone in the derived category, and this limit is a homotopy limit. All right. So that's some basic object, and okay, what do I want to ask? I want to ask a question about it, and it's motivated by the following fact. So this Rham complex, it's characterized very nicely by a universal property. There's a universal property for the ordinary Rham complex. What is it? It's that, so it's what you might call a strictly commutative DGA, differential graded algebra over R. What do I mean by strictly? It's a little bit of a subtlety. So strictly, I just mean that odd elements square to 0, which is non-obvious when there's two torsion. Okay, so but maybe just think of CDGA, and it as that structure, its initial for receiving a map. So initial such X receiving a map A to X naught, the 0th graded piece, map of R algebras. So it's the initial way of turning your R algebra into a commutative differential graded R algebra. So that's a nice universal property. And the question I want to ask is there some similar universal characterization of these derived variants? So is there some derived version of the Rham complex? So here it's important that it's not Rham cohomology that has a universal property, but the actual cochain complex up to isomorphism, or this actual CDG up to isomorphism has a universal property. There's some way to talk about that for the derived version. Okay, and I'll give a positive answer to, well, at least the Hodge completed part can be recovered. Okay, that's derived Rham cohomology. That's the one question I'll talk about today. And the other half is about Hochschild homology. Were there any questions about that? Please shout out questions if you haven't. Okay.
Yeah, sorry. Yeah, I have a quick question. So will there be any universal property for the Hodge filtration?
Yes, yeah. So yeah, I should have said it's going to be a universal property characterizing Hodge completed derived cohomology with its Hodge filtration.
With the filtration. Okay,
Yeah,
great.
it's important to keep that in mind as well. Keep track of that as well. Thanks. Okay, Hochschild homology, that's another construction. Now let me just start in the derived world. So it's going to take in a simplicial commutative R algebra. And okay, so it's some object HH A over R. What is it? It's another simplicial commutative R algebra. You can define it, a good way to define it is as the S1 tensoring in simplicial commutative algebras. And maybe a slightly more down-to-earth formula is this relative derived tensor product. Right, okay. So that's Hochschild homology. And this formula with the S1 tensoring, it tells you that there's an S1 a circle action on this object. So let me also mention that you can extract, there's a bunch of other invariants that you're probably familiar with. One of them is negative cyclic homology. HC minus. And that's defined to be the homotopy fixed points of Hochschild homology. Okay. Now, what is the real thing? So the real thing I was trying to understand in this project was the following theorem, which came before the project. So let me state it. There's a bunch of attributions, but let me just state it first. So it's a relation between these objects and the objects I introduced on the previous page. So there are filtrations. So firstly, on Hochschild homology, and what does this look like? It has associated graded given by derived differential forms. So the GER star is L omega star A over R. Oops, my A is still my simplicial R algebra. And there's a little shift. It's in homological degree star, or shifted by homological degree star. And I'll say a little bit more about that in a second, but there's also a filtration on HC minus. And now the associated graded is in terms of Hodge-filtered derived Rham cohomology. So this is what I was writing, L omega greater than or equal to star A over R. And there's still a shift, but there's a shift by 2 star. Okay, so there are these filtrations that sort of on associated graded look like these de Rham invariants. Okay, so this first one, it's called the HKR filtration. It sort of starts with the classical HKR theorem, Hochschild, Custon, Rosenberg. In what sense does it start there? So for A smooth over R, this filtration, it's just the Postnikov filtration. By that, I mean, it's a filtration where the associated graded are just the homotopy groups of the simplicial commutative ring. And why are the homotopy groups this? Well, Hochschild, Cosson, Rosenberg tells me that the homotopy groups of Hochschild homology are just differential forms in the smooth case. So in the smooth case, this filtration is just the Postnikov filtration, and in general, one obtains it by this non-abelian derived functors or left Kahn extension procedure. So I read about that in the work of Botmar Schulze, but I think this was written down in some form by Quillen as well as in the form of a spectral sequence. But yeah, let me also mention that, well, okay. Right. Okay. So that's the HKR filtration on Hochschild homology. This filtration on negative cyclic homology, at least in this integral in this arbitrary over an arbitrary ring, is much more recent. That's due to Ben. And there's similar ideas, but it's sort of there's also more ideas. There's also more ideas. So you do something in the smooth case, and then you left conic stem. But yeah. Well, let me not say too much in detail about it. But yeah, let me also mention the work of Ottmar Schulze here. So sort of p-adically completed versions of these results are some basic input in their work on topological Hochschild homology and integral p-adic Hodge theorem. Okay, so this is some result that relates Hochschild invariance to de Rham invariance. And one might ask, what is a real reason? What is the conceptual reason that this happens? And sort of the reason you might expect that there is a conceptual reason for this is that just like the de Rham complex is characterized by universal property, so is Hochschild homology. So there's a universal property for Hochschild homology for this S1 tensor ring. It's the initial simplicial R algebra with S1 action X with a map. The simplicial R algebra is non-equivariant A to X. And let me note right away that so I phrase this in a way that should look very analogous to the universal property for omega dot. So in the analogy, the simplicial ring structure is like the commutative graded algebra structure, and the S1 action is like the differential. Okay, and so maybe I should say I learned this analogy from Lars Hesselholt, and okay, yeah, so it's very suggestive, and it looks like these universal properties should explain the whole story, but that's not really the case, or that wasn't really the case. So that leads to a question. So can one construct or characterize or understand these filtrations purely in terms of these universal properties? Okay, and that's sort of what I really want to explain today. At the same time, I'll answer the question not from the previous page, but sort of the motivation for characterizing derived Rham cohomology by a universal property was to see what's sort of the formal reason that it shows up in Hochschild homology in this way. Okay.
Sorry, just to make sure I understand so it doesn't work to compare universal properties before passing to filtered objects, but then the game is when you work in the filtered category, then it does work, or?
Yes, I mean, so something you can say right away from the original universal property is like, so if you have a discrete R algebra A, then there's a map from, you automatically know there's a map from the de Rham complex into the homotopy groups of Hochschild homology. That's sort of, you can't formally prove that that's an isomorphism. I mean, you have to do some kind of, well, it's an easy calculation, but you have to do a calculation to show that's an isomorphism in the smooth case. And what I'm arguing here is that like in the there's a stronger universal property in the filtered setting where sort of you'll get isomorphism, you'll get real identifications automatically. So yeah.
Okay, great, thanks.
One more question from the chat. Is there an analog of HKR for negative cyclic homology?
Maybe you have something else in mind, but I sort of think of this filtration as an analog of HKR.
Do you have something more to say when A is smooth in this case? maybe that's a question to Ben.
I don't know anything more. Yeah, I mean, so it's not like the homotopy groups of HC minus are. I think it's really, well, because yeah, you can see what this filtration says, but that's all I know. You can ask if the filtration splits and so on, but I don't think that happens in general. Yeah, maybe Ben has something more to say.
Oh no, I mean, maybe you can say something in characteristic 0, but.
Right. Yeah, so maybe I want to mention, yeah, in characteristic 0, this was done earlier by Toe and Vitsosi. This work is sort of how to extend this to the integral setting. And I also want to mention the work of Molinos, Roballo, and Toen. So they basically have another take on the same ideas that I'll talk about. Okay. Good. Okay, so what's the game? The game is find all the structure possible on the HKR filtration. And then we'll see that characterizes HKR filtered Hochschild homology by universal property and we'll see sort of what happens with the de Rham story at the same time. So I'll really sort of start with the second question, and the first question that I asked will fall under fold. So the first structure I want to talk about is this idea of a filtered circle action. Let me first just set up the basic concepts for working with filtered and graded objects. So let me let Phil of D of R. This is the filtered derived category. So in the infinity categorical world, this just means Z-op index diagrams in the derived category. So, okay, let me just write an example so you know what I'm talking about. So something I already discussed, a basic example is the Postnikov filtration. So if I have an object in the derived category, then I can extract tau greater than or equal to star of m. So what is this? So it's a diagram of maps consisting of these canonical truncations. Sorry, of my object. Okay, so that's what a filtered object is. And a graded object, curve D of R, it's a diagram indexed by, so here in the filtered world, Z has maps in the category, and now I'm gonna just take a Z indexed collection with no maps. So that's the discrete category ZDS. So this is just a Z index collection of objects in the derived category. And there's some constructions, important constructions here. So there's an associated graded construction, GR from Phil to GR, which I've already been mentioning. So you get a graded object from a filtered object by taking cofibers of the maps in the filtration. So those are the successive quotients. And then I also want to mention that there's an underlying object functor, which I'll denote here, und. So that takes a filtered object and gives you a normal object, sort of the thing that your filtration is on. And formally that's given by the colimit of this diagram. So it's yeah, okay. just some setup. Okay, so here's a question. So suppose given an S1 action on M in the derived category, what structure is there on the Postnikov filtration? Why I'm at, so this is sort of the basic thing that happens in the HKR filtration. Classically, you have Hochschild homology of a smooth algebra. That's something with S1 action, and you're taking the Postnikov filtration on that. And I sort of want to understand what structure is on. So I'm trying to understand what structure is on the HKR filtration of Hochschild homology. So maybe a first answer, the most immediate answer. So what is M? M is just you can think of it as a diagram indexed by BS1. And so just by functoriality, the filtration is also going to be a diagram indexed by BS1. So the Postnikov filtration is also going to live as something indexed by BS1. In other words, I'm just saying that just by functoriality of the Postnikov filtration, if I have an S1 action on M, then all the maps in the Postnikov tower or this Postnikov filtration are going to be S1 equivariant. So this is something you might call an S1 equivariant filtration. That's the first answer one comes up with, but I'd like to suggest a better answer or some more structure. So instead of thinking of an S1 action in this way, I can think of it as a module structure over the group ring. So this is the normal story for group actions in the linear setting. I can think of M as a module over the group ring R adjoin S1, which might sound more familiar if I write it as chains on S1 with R coefficients. So an S1 action is this, maybe let me give myself some room. So an S1 action is the same thing as a modular structure over this. Okay, but now a sort of a better answer is suggested. When I take Postnikov filtrations, I'm not going to just get a module, something S1 equivariant. I'm going to get something a module over the Postnikov filtration of this thing, of this group ring. So the Postnikov filtration on M is going to be a module over Postnikov filtered group ring in the filtered derived category. So what does this look like? Looks pretty simple as a filtered object. The group, so chains on the circle has two homotopy groups in degree 0 and 1. So all this looks like is there's a bunch of zeros for a while, and then I have the fundamental class of the circle in filtration degree 1, and then I have the whole circle below it. So I've just done this little maneuver of putting the fundamental class in filtration degree 1. But that is really encoding something more. It's saying that when I have a module over this thing, it's like saying I have a circle action where the action of the fundamental class increases filtration degree. So let me write that down. So what is this encoding? It's saying that the action of the fundamental class of the circle increases the filtration degree. And you can think of this as analogous to the compatibility between the differential and the grading in a cochain complex. So the D and the G in a DG object. The differential increases the grading by 1. And here the circle action is increasing the filtration by 1. So let me use some names. So I'm going to denote this linearized circle by T, and this Postnikov filtration on it is what I will denote T fill, and this is what I'll call the filtered circle. And this module structure in the filtered world over the filtered circle is what I mean by a filtered circle action. So this is some structure present on the Postnikov filtration of any S1 equivariant object in the derived category. Okay, so this is some moral way to think about it. Let me also make a remark, another remark about how to think about it. So what does it look like on associated graded? So what is the associated graded of a filtered circle action? Well, it's a module. So well, it's a graded module over the associated graded of the filtered circle. So what does that look like? That's another. It's a simple graded object. There's only two graded pieces. Well, there's a fundamental class in grading 1, and then there's the 0th homotopy in grading 0, and nothing else. So there's a unit object in grading 0, and there's a square 0 element in grading 1. So I'm going to call this D. I call this D plus. The plus because the epsilon in this square 0 thing is in homotopy in a positive homotopy degree. Okay, so what is a module over this thing? Well, what is a graded module? So first of all, it's a bunch of xi. It's a bunch of complexes. And then the module structure is encoding, so there should be some map from D from xi shifted by 1 to xi plus 1. And this is a square 0 algebra, so there's some specified homotopy, D squared is 0. And there's a bunch of other homotopy-coherent structure coming from the fact that I have a coherent module over this thing. In other words, it's a homotopy. So this is exactly what you might think of as a homotopy-coherent cochain complex in the derived category. So it's well, you might call it an H plus cochain complex, or H plus DG object in the derived category. Here I'm using H plus to indicate this this shift that happens in the differential. Okay, so just to recap, so the associated graded of a filtered circle action is a homotopy-coherent cochain complex, and on the other hand, the underlying object of the filtered circle is just this circle. That's clear. So underlying the filtered circle action is a usual S1 action. Okay, so I'm trying to express that filtered objects are sort of interpolations between their associated graded and underlying, and this notion of a filtered circle action is an interpolation between the notion of a coherent cochain complex in the derived category and a circle action on an object in the derived category. All right. Any questions about that? Okay, so that's one of the main pieces of structure that I wanted to introduce. today, and it's not all you need to formulate to sort of answer the questions I stated at the beginning of the talk, but let me state the theorem that answers those questions to motivate the rest of the structure that you need. So let me state the theorem with everything not yet defined. So A is a simplicial R algebra. So first, regarding the HKR filtration on Hochschild homology. So it's going to have one of these filtered circle actions, but it's going to be more. It promotes to a, this is not yet completely defined, a filtered simplicial commutative ring or simplicial R algebra with filtered circle action. And in fact, it has a universal property as such. In fact, it's the initial such receiving a map from A to the underlying. So such a thing has an underlying simplicial R algebra and it to receive a map from A. So it's exactly a filtered analog of the universal property of Hochschild homology. And this is slightly a lie. So I need, in this universal property, I need my filtrations to live in non-negative degrees. So in that case, the underlying is just like the 0th piece of the filtration. Okay, so that's the universal property of the HKR filtration. And for the Rham complex, so the L omega star, so the derived differential forms, this graded object, it promotes to one of these coherent cochain complexes. And in fact, it promotes to a, again, there's an algebra structure as well. So there's an H plus DG, it's like a differential graded simplicial commutative R algebra. Maybe I wanted to write that in blue. And again, it has the same universal, or similar universal property. In fact, it's the initial such receiving a map. Simplicial commutative algebras from A to the 0th piece. So this is it's exactly a derived version of the universal property of the usual Rham complex. Okay, and so I think I won't have time. I've chosen not to emphasize this part of the story today, but let me just make a remark. From these structures, you can recover the filtration on negative cyclic homology and Hodge completed derived Rham cohomology with its Hodge filtration and the relation between the two. And let me just say one word about it without really going into it. So what happens is this HKR filtration, I'm characterizing it as something with filtered circle action, and the way you get a filtration on the homotopy fixed points is you do something called filtered S1 fixed points. So this additional structure of a filtered circle action lets you recover the filtration on negative cyclic homology as well. Okay, but for the rest of the talk, I sort of want to explain what are these algebra structures that are the other important part of this. The other important structure in this theorem are these algebra structures compatible with the circle action and coherent cochain complex structure, and I sort of want to explain how to formulate that. Okay, but this is sort of the theorem that answers the questions that I said before.
Sorry, may I ask a silly question? So
Yes.
as far as I understood, the difference between the filtrations on HH and HC minus was that you cut the derived Rham cohomology, don't you? Right.
So HH, the graded pieces are just the differential forms, L omega I, the individual forms, and for HC minus, it's parts of the Rham cohomology.
Yeah. So is there some easy way to see why when you take homotopy fixed points on your filtered S1 action story that somehow instead of
Yeah, I think I understand the question. Yeah, it's easy once you think. It's easy once you think about it. So the story is sort of like, so there's an analog of the filtered S1 fixed points in the graded world. It's like filtered, or sorry, it's like graded D plus fixed points. I mean, that's what you would write down if you were just pattern matching or something. And there's a nice story here that graded D plus fixed points, it's sort of exactly is the operation of extracting the cohomology of a homotopy-coherent cochain complex. That's something I could explain further, but yeah.
Okay, thank you.
Yep. All right. Okay, so now let me discuss ring structures. Right, so what I want to, so what I haven't formed, I need to formulate what it means to have a filtered simplicial commutative ring compatible with a filtered circle action. And this is supposed to be analogous to the fact that in a commutative differential graded algebra, all the structure present is compatible in some way, like there's a Leibniz rule that tells you how the differential interacts with multiplication and so on. So how am I going to do this here? Well, let me first say, so for S1 actions, so just for normal S1 actions, things are easy in the language of diagram categories, easy in terms of diagrams. So in the universal property of Hochschild homology, I did talk about a simplicial commutative ring with S1 action. And this is, well, I can talk about this in this usual way. So instead of talking about BS1 shaped diagrams in the derived category, I can talk about BS1 shaped diagrams in the category of simplicial commutative R algebras. But now in this filtered and graded world, I'm no longer in the situation where I have a diagram category. I need to ask myself how to express this purely in terms of modules over the linear circle. Because in the filtered and graded world, I've defined my objects as modules over linear objects that don't come from. Basically, I shouldn't be allowed, I'm not allowed to talk about S1 the space anymore. I only have access to the linearized object. Okay, so this is sort of a, okay, so I'll answer how to do it in the filtered and graded world by first asking myself how to do it in the normal world. Okay, so maybe a warm-up question. Is how to do, so maybe this, depending on what kind of person you are, this sounds more complicated, but I think it's easier to think about how to do this for E-infinity algebras rather than simplicial commutative algebras. And the point is, so here the question is, what does the pointwise tensor product on S1 representations in the derived category mean in terms of modules over the group ring. And so E-infinity algebras, they're commutative algebras for this symmetric monoidal structure, this representation, this tensor product of representations. But I want to be able to, I want to understand what does that mean in terms of modules over the group ring? How do I get that symmetric monoidal structure on modules over the group ring? And okay, so the answer to this, if you've thought about group rings before, might be familiar. So it's induced, the point is that there's more structure on the group algebra than just an algebra structure. There's a bi-algebra structure or a Hopf algebra structure. One color. And it's in fact, well, so it's important that it's co-commutative here. Co-commutative bi-algebra structure on this group ring. Where does it come from? So where the coproduct so this is the group ring on S1, and this is equivalent to the group ring on S1 times S1. This is coming from the diagonal map. So the point is that if I have two modules over the group ring, I can tensor them together over R, not over the group ring, and get a module over T times T tensor T, and then I can pull back along the diagonal to get a module over T again. This is how to encode the tensor product of representations in terms of group rings. And if you want to spell this out formally, the important structure on T is that it's a co-commutative bi-algebra. So that explains how to get E-infinity algebras. How would you get simplicial commutative algebras from this picture? So morally, simplicial commutative algebra structures are a stricter version of commutative. So it's more strictly commutative algebra structure than E-infinity algebra structure. So this suggests that if you want to formulate simplicial commutative algebras over the group ring, so for simplicial algebras, what do we want? An even more co-commutative. So some analogously more co-commutative bi-algebra structure. Okay, so I thought about that and I didn't know how to do that. I think I now have an idea about how to do that, but it's a weird question, and there's a well, I think there's a more natural answer, sort of, that comes from a shift in perspective. So okay, so this is kind of a weird thing, but here's an alternative that's more natural, I think. Alternative warm-up answer. So the alternative comes from pulling, oh, not projective space. Pull a little switcheroo. You consider the dual object, T dual. So that's the cochain algebra of the circle. And you do this weird thing. So modules over T, so modules over chains are the same thing as comodules over cochains. So a circle action can also be encoded as a comodule over cochains on the circle. And now dually, T dual. So what's important dually is that there's a commutative bi-algebra structure. So the bi-algebra structure dualizes, And why is this dualization good? So from this perspective, there's an interesting characterization of commutative algebras now. So commutative or E-infinity algebras in the comodular category. So yeah, I can write them as comodules in the commutative algebra category. So what happens? So I'm saying that T dual, it's a commutative bialgebra. I can think of that as a coalgebra in commutative algebras. And I'm saying a commutative algebra with S1 action, you can think of it as a comodule over cochains in the commutative algebra category. And this suggests sort of a cleaner answer to what we want. So it suggests a different answer. It suggests that we want a simplicial R algebra structure on cochains so that simplicial commutative algebras with S1 action are the same thing as comodules over a T dual in simplicial commutative algebras. So, you know what I'm saying? Once you dualize, it's clear what you need to strengthen. You need to strengthen something from a commutative algebra structure to a simplicial commutative algebra structure. That's what we want, but again, we face an issue. And the issue is that, so simplicial algebras, well, the desire makes no sense. So simplicial algebras are connective objects. And T dual is not. Okay, but there's a solution. And this is this theory of, well, so a theory, you want a theory of non-connective, you want to enlarge the theory of simplicial commutative rings in a way that allows for non-connective objects. So non-connective simplicial rings, which I'm going to call derived rings. So this is a real thing due to Akil. And I think also the subject of ongoing work of he and Bhargav Bhatt. So yeah, there is this notion of a non-connective simplicial commutative ring, and okay, so I want to say a few words about that. So what's the idea? So simplicial commutative rings, they live over connective objects in the derived category. And what I want is something analogous living over the whole derived category. Called derived rings, derived algebras. And the way it's formulated is that you think of simplicial commutative rings as algebras over a monad. Sorry. Water. Algebras over a monad over the connective derived category. So there's a free simplicial commutative algebra functor, the derived symmetric algebra functor, and this category is this adjunction is monadic. So I can think of simplicial commutative algebras as algebras for this L sim monad, and it turns out. So yeah, the strategy is you extend the monad to the whole derived category and consider algebras over that. So let me write that. The monad LSIM extends canonically to the whole derived category. And this is by the theory of polynomial functors. Following ideas of Lucas Brandner. Okay, so let me not say a lot more about that. Let me just maybe say that one important example. In this, so that this lets you do is you can take limits. So if you have a limit of a diagram in simplicial commutative rings, it's better taken inside this category of derived rings, because the limit might introduce negative homotopy, and you might want to remember that. So one example is, in fact, this cochain algebra T dual RS1. So this is the limit of the constant diagram of shape S1 with value R. So indeed, this cochain algebra, it's a good example of one of these derived rings, and this lets you formulate the thing that I wanted to formulate. So derived rings with circle action are in fact the same thing as comodules over this cochain algebra in derived rings. All right. So that was this long solution to this problem, how to formulate S1 equivalent algebra structures purely in terms of the group ring. The answer was, well, you dualize and then you formulate these derived ring structures on the dual. Okay, almost out of time, but let me say at this point, so you can formulate in a very similar fashion with these derived symmetric algebra monads, filtered and graded versions of derived rings, and prove that the Postnikov filtration functor it sends co-connective derived rings to filter derived rings. And as an example, the filtered circle, so the dual of the filtered circle, which is the Postnikov filtration on cochains, is a filtered derived ring. And that lets me run this whole story again. So now I can define this. I can define this notion that was undefined before, a filtered simplicial or a filtered derived ring with filtered S1 action. It's a comodule over. It's a comodule over this object in filtered derived rings. And the story for graded, so these differential graded simplicial commutative algebras is similar. Okay, so this sort of, well, I haven't explained everything, I guess, but this is how you formulate all the structures you need just in the theorem in the main theorem that I stated. And let me just wrap up in a minute by saying, once you have these structures, what do you do? It's very, well, the point is that it's very formal once you've formulated these things. You define a filtered version of Hochschild homology by the universal property I stated in the theorem, and you define an object L omega dot by the universal property I stated in the theorem. So you define these objects by universal properties. They exist by abstract nonsense, and then prove, again, entirely by nonsense, that one L omega dot is what you want it to be. It really is something encoding derived Rham cohomology. And two, that the associated graded of a HH fill is L omega dot, and that the underlying is Hochschild homology. And the point is that these equalities are are evident from the universal properties characterizing all the objects. Okay, and that's what I wanted to do. Thanks very much.
And now, are there any questions?
I have a question, maybe an obvious one probably. For what about formulating some of these things for in the sort of topological setup for THH?
Yeah. I'd love to answer. I've thought, I mean, that's really what I wanted to do in some sense. This was supposed to be the warm-up, but I haven't figured out how to do that yet. It's the main obstacle I can say is that one thing that this makes clear is that simplicial commutative algebra structures are very important in this story. The input should be a simplicial commutative algebra structure, and the structure you want to keep track of is something like a simplicial commutative algebra structure. And in the THH story, a very important thing is that THH of FP is an E-infinity algebra and not a simplicial commutative algebra structure. It's not a simplicial commutative algebra. Somehow you need to make these two worlds talk to each other well, and I haven't figured out how to do that.
What if you restrict your attention to characteristic P?
Right, even in that case, yeah, I mean, yeah, even in that case.
Yeah, I guess maybe especially obviously in that case.
Right, I mean, the main thing is THH of FP somehow, yeah. It lives over Z, but it's not a simplicial commutative algebra.
Can I throw in a question?
Yes.
I have to run to a meeting, but for me, the filtration's especially interesting because characteristic classes lie in different filtrants. Do you gain any insight into why, say, the kth Chern class lies in the kth filtrant from this approach?
I think I don't know. Yeah, I'm not sure. I haven't thought about that.
All right. Well, let's all think about it. I'd like to. Yeah, I'll learn your stuff. Okay, great. Got to run. Bye.
Bye.
Any other questions?
I also have one about something you actually talked about. These H plus DG objects in the derived category. I don't think I really appreciated them. If I have an actual chain complex and not a representative of an object in the derived category, do I get one of these or?
Yes, you can get one by you get one where but you have to shift the terms sort of. So if I have an actual, so for example, the Rham complex, there's a, well, okay, maybe I should say the example. So let's think about the actual Rham complex of a smooth algebra. So that's related to the associated graded of HH of the smooth algebra. So, but the associated graded of HH is sort of a shifted version of the Rham complex, right? So the terms are omega I shifted by I. And in general, so I can do that with any complex. There's some H plus complex with terms like xi shifted by I if I have an actual cochain complex of modules. But yeah, the point is that away from the smooth case, when the L omegas are not discrete, these things are sort of not coming from normal cochain complexes of modules.
Good. Any other questions?
Sorry, so I was just wondering, so this notion of the filtered circle, so right now it's defined over the integers. Is it possible or expected that it would lift to the sphere?
It definitely does not lift to the sphere. Or, well, I guess you have to specify what structure you want to lift it. And so, for example, like even if you want something like so if you want it as a or a bialgebra with the structure that I talked about, it doesn't lift to the sphere. It does lift to little ku. The E infinity version of it does lift to little ku. But again, the E infinity version is sort of not enough to talk about the things you really want to talk about. It doesn't even lift to like anything above height 1.
What's special about height 1?
It's sort of, you can think about the circle as, let me put it this way. So lifting the filtered circle is like equivalent to lifting filtered CP infinity in some sense. And you sort of want to lift a filtration of CP infinity as an E infinity algebra. And if you look at, that sort of means that the formal group law can only live in some very small filtration degrees. So the formal group law is going to only have terms involving very small powers of, can't be complicated. It can only be multiplicative or additive, basically. I don't know if that makes sense. But...
Great.
Thanks.
What about Hochschild cohomology? There is no circle, but there is HKR. Can you say something about that?
Yeah, I confess I haven't thought about it. Yeah, I'm not sure.
I see. Okay.
Great. Well, let's thank Arpon again, and then we'll hang around for a few minutes if people want to chat a little bit more. And otherwise, I'll see you all in 2 weeks for Paramala's talk.
Yay, thank you for the talk, Arpon. Cool stuff.
Thanks, Maria.